What I want to share today is not a new technology and is not a silver bullet. It's a way of thinking about oil in water emulsions that consistently reduces complexity, energy demand, and risk. This session is about connecting formulation science, interfacial behavior, and processing in a way that actually works at scale. In formulation, nothing replaces hands-on experience. Across more than 2 decades working with global and local brands, one lesson remains constant. Formulation is learned through real systems under real stress. When emulsions fail, we tend to look at the equipment first. But in most cases, the real causes sit much earlier in formulation design and in how we apply shear. Across the industries represented in this room, the pressures are remarkably similar. There is a push to deliver emulsions that are stable, while at the same time reducing energy use, avoiding overspecified equipment, and scaling reliably from pilot to production. Inline multi-stage shear is often discussed as an alternative to high-pressure homogenization, but it only works properly when formulation and processing fundamentals are aligned. Without that alignment, changing equipment just moves the problem around. Oil in water emulsions are, by definition, thermodynamically unstable systems. They only exist because we introduce an energy barrier that slows down the natural tendency of the system to reduce interfacial area. Emulsions are metastable rather than stable. Droplets are always driven to merge. Density differences promote criminal sedimentation, and polydispersity accelerates ripening processes. If the interfacial film is not sufficiently cohesive and elastic, it will eventually fail under these forces. This is not an accident or a processing fault. It is the baseline behavior of the system. Accepting these changes how we approach formulation and scale-up. The objective is not to eliminate instability, which is impossible, but to control the kinetics of the stabilization by engineering the interface correctly from the start. This is another design tool. It's a reminder of constraints. Emulsifier selection, oil phase composition, ionic environment, temperature profile, and ingredient order determine the interface and form rapidly and remain resilient. If absorption kinetics are slow or the interfacial film lacks elasticity, coalescence is effectively locked in from the first droplet. Processing cannot reverse this. It can only accelerate the outcome. This is why formulation issues so often reappear during the scale-up, despite changes in equipment. Stability problems are rarely created by processing. They are exposed by it. Early formulation decisions can carry far more weight than is often acknowledged. In practice, there is a clear transition point in emulsion development. Once formulation has established a viable interfacial window, processing becomes the dominant factor shaping final behavior. At that stage, processing determines droplet size distribution, interfacial coverage, sensory profile, and long-term stability. What is important to emphasize here is that this transition does not mean processing can compensate for formulation weaknesses. It can only rebuild them. When emulsions fail during scale-up, more often than not, is because the formulation never created an interface robust enough to tolerate what processing inevitably applies. Across multiple systems and sectors, the same patterns appear. When formulation decisions create the optimum formulation characteristics, processing refines it. When formulation decisions push the interface close to its limits, processing simply accelerates the outcome. Multi-stage inline mixers change the equation because they apply shear in a fundamentally different way. Instead of a single intense deformation event, droplets experience repeated controlled deformation as they pass through each stage. Every droplet is exposed to comparable shear conditions, which dramatically improves uniformity. The result is not simply smaller droplets, but narrower droplet size distribution, reduced coalescence, and improved reproducibility. Processing times shorten, energy demand decreases, and scale-up becomes simpler because performance is driven by geometry rather than by brute force. This is where engineering design, rather than speed or power alone, become the dominant variable. At this point, it's important to explain where these conclusions actually come from, because the geometry choice was not intuitive, and it certainly wasn't arbitrary. But Kimson carried out a systematic CFD study looking at a wide range of rotary stator tooth configurations rather than focusing on a single design. In total, dozens of geometries were evaluated by varying three primary parameters: tooth height, number of channels, and channel width. All simulations were run under the same operating conditions, so the effect of the geometry could be isolated from speed or flow artifacts. What became very clear from this work is that emulsification performance is not governed by peak shear values. You can generate very high shear locally and still have poor emulsification if only a small fraction of product ever experienced this. The key outcome was understanding shear distribution, not shear maximum. The CFD maps show that tooth height primarily controls shear intensity, while channel number and width control how much of the total flow is exposed to that shear. Lower tooth heights increase shear rate, but without sufficient channeling, the shear remains spatially limited. Increasing the number and width of channels dramatically increases the volume fraction exposed to effective deformation. The HSM6 configuration sits at the point where these effects balance. It does not maximize trims, it maximizes the useful shear exposure across the bulk of the flow, while still operating within a realistic pressure window that makes industrial operation feasible. This study provides confidence that the geometry is doing the right work at the right place for the right proportion of the product. From an emulsification perspective, that reduces the number of under-processed droplets, which are typically the ones responsible for the broad size distribution, recoalescence, and early instability. What matters in this case evidence is not the absolute droplet size achieved, but the pathway by which this is reached. The formulation and interface are within the right window. Multi-stage inline shear tightens droplet size distribution because a much larger fraction of the product experience effective deformation. This reduces recoalescence after breakup and improves long-term stability without increasing energy input. The real industrial benefit is predictability. The process becomes less sensitive to formulation variability and operating fluctuations, which is critical when moving from pilot development to sustained full-scale manufacturing. When these patterns are taken into manufacturing practice, a few principles tend to hold consistently. Stability improves when the interface is treated as a design constraint rather than a consequence. Emulsifier systems that are compatible with the full oil phase composition, including actives and fragrances, behave far more predictable under shear. Sensitivity to pH, ionic strength, and temperature needs to be understood early, because the small shifts in these parameters are often what pushes the systems over their stability limits. From a processing perspective, emulsification becomes more robust when the objective is uniform exposure rather than a maximum intensity. Processes that minimize poorly protected droplets early on and operate within defined flow and pressure windows tend to be easier to scale and troubleshoot. Validation is also more effective when attention is paid to droplet size distribution and stability behavior over time, rather than relying on average size as a single performance metric. These are not prescriptive rules, but recurrent patterns that reduce unnecessary iteration in the real manufacturing environment. At this point, I don't want to offer prescriptions. The value of this topic lies in recognizing patterns that many of us have encountered repeatedly in manufacturing. Emulsions that fail rarely do so for random reasons. Instability almost always emerges from misalignment between formulation, interfacial behavior, and how shear is applied in practice. When those elements are aligned, the stability becomes predictable and the scale-up far less painful. When they are not, complexity and energy escalate very quickly. If this framework reflects challenges you are currently facing, it's often useful to discuss the specific systems and constraints because that's where the real insight usually emerges. Thank you for listening, and we hope that you get in contact with us for any questions.